Okay, let's start today's lecture. Okay, my name is Jung-Ho Park, and welcome to the Signals and Systems course. Previously, we are dealing with the properties of the Fourier transform in discrete time case. So most of them are similar to those we had done in continuous time. So the filter was one of the example that utilized the convolution property, and we also used this Fourier transform property to get the solution of the difference equation, more specifically linear constant coefficient difference equation. It has to be a linear constant coefficient to make the LTI system, and we did with the simple example. Okay, and mostly we talked about the modulation property, which is about the multiplication of two signals in time domain. If you do that and perform the Fourier transform, then you will have the shape of the convolution with only 2 pi integral. So it's a periodic convolution, whereas you will get the non-periodic convolution with continuous time. And one of the signals is expressed as -1 to the nth, and this signal is very simple, so that we can determine the coefficient of the Fourier series in a very simple way just by comparing the synthesis equation and the exponential form like this. So the Fourier transform can be obtained by a bunch of shifted impulses like this, and we get 0 for 0 radian per second and 2 pi for pi. And if you try to compute this x1, which is -1 to the nth, and x2, which is just a general input function, then with the Fourier transform, you will have to do this convolution in frequency domain. And the convolution between a general signal and the shifted impulse results in the shifting of this x2 onto the place where the impulse function is located. So in conclusion, like multiplying -1 to the nth to some signal may result in the shifting by pi in the frequency domain, not in the time domain. So this signal gets like this because you literally multiply by -1 to the nth, so the signs get changed depending on the value of n, like this. However, this thing happens to be shifting the Fourier transform by the pi, and pi means like from low frequency to high frequency, because in discrete time signal, the Fourier transform gets repeated for every 2 pi. We can use this example to implement a high-pass filtering effect with a low-pass filter. This was the last part that we did. And like this is the case. We studied and designed and put a lot of effort to design this low pass filter, and we don't want to do that again. So we would like to use this low pass filter to have an effect of high pass filter. That's what we are trying to do in the last second of the previous lecture. So since it's a low pass filter, it will pass the values which are located at low frequency in the frequency domain. So for example, if the magnitude of the Fourier transform look like this, like a Gaussian function, then if you pass through the low pass filter, this part survives, whereas this part get removed. And I would like to have a high pass filter with the same low pass filter, which means I want to have this kind of red line as a final result. So to do that, I try to multiply the original signal by -1 to the nth in the time domain, which will result a shifting onto the plus pi by the amount of plus pi. So I had this one also because we have to repeat at every 2 pi for the discrete time signal. Remember, there was a periodic. There is a periodicity for this discrete time signal. And if you do that and apply to the same LPF system, then because it's the same low pass filter, you have to pass through the stuff around 0. So this is the case. However, this is not even close to this result, so I had to do the multiplication of -1 to the nth one more time to fix this frequency response to the original one like this. So in summary, to make a high pass filtering effect by the low pass filter, you have to multiply -n to the nth right before the input and right after the output. I mean, you have to do it for twice. That's the point of this example application. So today, before moving to the next chapter, I would like to have a summary for continuous time and discrete time. Okay, so continuous time Fourier series the periodic signal xt can be obtained by the infinite summation of ak e to the, so this summary I have to write it right, so ak e to the j k omega 0 t, remember? And that ak can be obtained by 1 over t0 integration for one period xt e to the minus k jk omega t dt, like this. So this is the equation about the continuous time Fourier series. And also, we extended this to the continuous time Fourier transform. And to obtain the non-periodic signal, non-periodic continuous time signal, then we have to do this 1 over 2 pi times integration of infinity x of omega e to the j omega t d omega. We can obtain the Fourier transform of this continuous time by having this integration. Okay? Also, we just finished the discrete time. So discrete time Fourier series. So since I'm talking about discrete time Fourier series, it should be, the x should be periodic. So xn can be represented by the summation of just one period. So you don't need an infinite number of coefficients. And you can have this expression. And AK will be 1 over n summation of n where I can have this expression. So this is two equation for the discrete time Fourier series. Finally, the discrete time Fourier transform, we have the equation of 1 over 2 pi and integration for just one period e to the j omega and d omega like this. And even though we're talking about discrete time, its Fourier transform was continuous and also periodic. Remember, this was a very important factor. And we can complete this equation like this. So, okay, so one by one, this was about Fourier series. So x should be what? It should be periodic. And you need infinite number of coefficients. And we cannot guarantee that AK is periodic, right? We side with the examples. So the AK for the continuous time Fourier transform is non-periodic. There's no guarantee that it's periodic, right? And also, for the discrete time Fourier series, since we're talking about Fourier series, x should be periodic discrete signal. And contrary to this part, you need finite number of coefficients to express this periodic signal. And with this discrete time property, AK was periodic. You have to see this difference. Also, for a continuous time Fourier transform, we are dealing with non-periodic signal. And as a result, the Fourier transform was also non-periodic. So like this integral is like a lot of like summation, right? Like infinitely many summations. So it's represented by a summation, infinite number of summation of the frequency value. And also, we are talking about the Fourier transform of discrete time case. Therefore, this xn should be non-periodic. However, interestingly, the Fourier transform of this non-periodic discrete time signal is continuous as well as periodic. And you need infinite number of them. Okay, so we checked about this period, and what I also want to do is check the duality. Do you remember the duality property that we discussed during the continuous time? So duality was about if you conduct the Fourier transform once and conduct it twice, then you will get the same signal. Even though you have to reverse the x-axis, frequency axis, and also you have to multiply by 2 pi. I know that's true, but the basic idea about the duality is like if you double Fourier transform, then you get the original one. Okay? So that was the idea of the duality. And I really want to check the duality between these 4 groups. So I will indicate duality like this. Okay? So we just studied, in the continuous time Fourier transform, the page that we just visited was about the duality between this time domain of continuous time and the frequency domain of this continuous time. So yes, this xt and x omega has a relationship of this duality. If you carefully look at these two, xt is made of the summation and ak is made of this integration. So they cannot be in the relationship of the duality because of summation and integral. Also, I can say for the Fourier transform, discrete time Fourier transform, this xn is in discrete time space and this x of omega is in the continuous time space. Therefore, these two cannot be in the duality form because of the difference in the time space. Okay, one is in the discrete time and one is in the continuous time. Of course, the integration and summation is different. So if you carefully examine this discrete time Fourier series, these two are in duality position. So this xn and ak are in duality relationship. Yes. Okay, so do you think this is all that we can find for the duality between these groups? Actually, you can find one more duality relationship among these 4. So these are in the relationship of duality, and these are in the relationship of duality, so they are okay, and they are not okay. However, we can find between this and this in duality relationship. And I will describe it right here. And what do you think the duality occurs? Where the duality occurs? We can point out that we can start from here. I think we can start from here. So the Fourier transform of the discrete time signal is periodic and continuous function in frequency, and this periodic function is periodic, therefore it should have the Fourier series representation, right? And that Fourier series representation is the original sequence itself. I mean, so one more time again. The Fourier transform of this discrete time signal is a periodic function in frequency domain. And since it's periodic, it should have the Fourier series representation. And that Fourier series representation is the original sequence itself. Of course, I'm excluding the fact of reversing the x-axis and multiplying by 2 pi. So if I put that in words, I'm gonna write down with the abbreviation. So Fourier transform of discrete time signal. So the Fourier series of discrete time signal is periodic function, right? Of frequency. And since it's periodic, that periodic function will definitely have Fourier series representation because it's periodic, right? So if you put that continuous periodic function into this place, into this variable, then you will have the Fourier series representation, and that representation coefficient is the original sequence itself. Okay, so there is a hidden duality relationship between the continuous Fourier series and discrete time Fourier transform. So one more time, if you take any discrete time signal, it doesn't have to be periodic, you know. And if you obtained this Fourier transform of that discrete time non-periodic signal, then you will have a periodic continuous Fourier transform. And since it's periodic, you can obtain the coefficient for the Fourier series because it's periodic and of course it's continuous. And if you put that into this equation, then you will get non-periodic, some discrete time case where you have k as an x-axis, as we have studied before. That thing is the original x of n. That's what I wanted to tell you. Okay, so by summarizing this stuff, I think we can finish this chapter and move on to the next one. So the next chapter, I would like to talk a little bit more about the filtering, which is the application of the convolution property in Fourier transform. Remember? So I think we covered many things about the filtering already, but I would like to go a little deeper for this area. So utilizing the convolution property of Fourier transform, you will have a lot of theories, and one of the area is the filtering. So before moving on to the filters, I would like to quickly remind you about the convolution property. There are both continuous time case and discrete time case, of course, and if you have LTI system, then it will be represented by this impulse response, and if you do the convolution and their relationship, if it's converted into the frequency domain with the help of Fourier transform, then you will get h omega multiplied by x of omega. This was very good example, and you will have the exactly same effect with discrete time. Exact same property with this discrete time case. So if I go through this LTI system for continuous time, I can get the output just by multiplying it. And also, with the discrete time, I will have the same multiplication to get the discrete time output if you want to obtain the output in the time domain. And what is this called? This was called the frequency response in continuous time and discrete time respectively. So the Fourier transform, one more time, Fourier transform is made of the complex amplitude of complex exponentials. And by passing through this LTI system, it's like literally multiplying the frequency response to the complex amplitude. So the Fourier transform consists of complex amplitude with or of complex exponentials, because complex exponential was the basic function that we have adopted. And by by like passing through this LTI system means I'm going to multiply frequency response to this complex amplitude. So this means, the reason why I'm repeating this again is because we can separately touch the amplitude for respective complex exponential. So I can manipulate the amplitude of each complex exponential, and that's the basic idea of filtering. I think adjust, control. I can control. I can control the amplitude of each complex exponential separately by using this convolution property. And this is the basic idea of filtering. Okay? So what I mean by this is that I can like manipulate or control the amplitude for each complex exponential, which means I can suppress the high frequency domain, or on the other way around, I can suppress the low frequency domain, and I can do that just by using the frequency response of the LTI system. We will start with the ideal low-pass filter, high-pass filter, and band-pass filter that we already know. The left one is the continuous time filters, and the right one is the discrete time ideal filters. So the filters are like a frequency response, so it's a system, okay? That's why we use the notation H for both continuous and discrete time. So they are like frequency response, and recall that frequency response is the Fourier transform of impulse response. So you can say it's a system. You have an input, and the output will be the result of that filter. And you already know the difference between these two. As you can see in this figure, the discrete time case is a periodic signal where the period is 2 pi. So if you see this ideal low-pass filter, you can see that there exists a value 1 around 0, around 2 pi, and around minus 2 pi. And whereas the high-pass filter has values around pi and minus pi, and maybe minus 3 pi, like that. So low-pass filter is like the value around 0 radian per second, and high-pass filter, you have values around pi radian per second. And you can see the discrete time is periodic in frequency domain, and it is not periodic for continuous time case. And bandpass filter, as I omitted the description before, it's like passing particular frequency with the bandpass filter. So it's not the lowest part that you pass or the highest part that you pass. You are going to like specialize some of them, the range for you to pass through. So this is like particular frequency range. And same thing can be applied to the discrete time, but you have to like make it a periodic signal for the discrete time case, okay? So I'm gonna move on to the next topic because we did quite a lot of things for ideal low-pass filter and high-pass filter. The next thing I want to do is to check the impulse response of this ideal low-pass filter. And for continuous time case, you have this impulse response, and with the discrete time case, you have the similar one. So they are pretty much the same for both continuous time and discrete time. So this is the impulse response for continuous time and frequency time, and this is the unit step response, the step response of the ideal LPF and ideal LPF in the discrete time. So if I may, I think I'll put here. This is impulse response, meaning that we are in the time domain, whereas the first filter Fourier transform are in the frequency domain, right? And this too is the step response that we have learned in the beginning of the lecture. So step response, I will say. Also, it is in the time domain, okay? Okay, so I think we will start with the impulse response. So you have to notify that this is not the magnitude of the frequency response. So actually, in this case, h of omega is a real value. I mean, before that, x of t was a real valued signal, remember? In time domain. But here, this h of omega is the real value for both continuous time and discrete time. So to obtain this impulse response, what you have to do is you have to do the inverse Fourier transform. And the result is this value and this value. And if you carefully examine these two functions, they are even function, right? They are even function. They are symmetric with respect to y-axis for both. And also they are not causal. It is non-causal system for both continuous time and discrete time. I will write that down soon. And we have a infinite number of value. Even though it decreases, we have infinite number of value for both direction, like this. And this is a shape of sine x over x. Okay, so I'm talking about impulse response first, okay? So this one and this one. As h of omega is real value, if you do the inverse Fourier transform, then you will get the impulse response in time domain. And if you see the plot, then you can see that it's even function and it's non-causal. And also this ht or hn has the shape of sine x over x, which means you have infinite value in both directions, plus and minus. How do I know that this ht is non-causal? How do you know this impulse response is not causal? We can verify the causality of a system by seeing the impulse response, which we did in chapter 4. Recall that the system is causal if impulse response is 0 for negative t, remember? We point this out at chapter 4, I guess. But you can see that this is an even function, and even function means you have values for negative t. So we can notify that h of t or h of n are both non-causal systems. Okay, so the reason why this impulse response is a shape of sine x over x and also have infinite direction for both is because this h of omega is a real value and it's in shape of rectangular. That's the reason. If you do the inverse Fourier transform, then this shape and the real value property cause this sine x over x and infinite values for both sides. So if you look at this ideal low-pass filter, I'm just going to speak with the continuous time because same thing can be applied to the discrete time. If you carefully look at this, the ideal LPF is cutting the frequency where this omega c is a criterion where to cut this frequency. I mean, from minus omega c to plus omega c, you're going to pass these values, the ones with this low frequency, and you're gonna eliminate the frequency which is higher than omega c and lower than minus omega c. So, however, in many filtering problems, it is very hard to establish this criterion, establish the standard where to cut. Okay, this is the first problem of this ideal LPF. So the first problem of the ideal LPF is that in many filtering problem, it is hard to establish the criterion where to cut the frequency. So this criterion is omega c in the figure. Okay? And also, if you look at the step response of this low-pass filter, oh, by the way, let's derive how to get the step response of ideal LPF. So I will start with that. So please keep in mind we have the first problem, and by using the definition of convolution, and we already obtained h, right? H of t or h of n, which is impulse response. So with two of these, we can obtain the step response. So with the definition of convolution, we can say ht is a convolution of x tau multiplied by ht minus tau d tau. So this is the definition of the convolution. And to obtain the step response, the input should be the unit step function, right? But before that, I can modify this dummy variable like this, remember? We can exchange the place of tau and minus tau like this. And so to have this step response, I have to put the input of unit step function. And please recall that the unit step function, the definition of unit step function is that if the original definition is that if tau is bigger than or equal to 0, then you have the value 1, and you have the value 0 for the otherwise. So this is the original definition. And if you want to apply it to this u t minus tau, then I always said you just put it in the original definition. Then you will have this for t minus tau. But you have to understand that the variable inside this integration is tau. So you have to look at the tau, which means if tau is smaller than or equal to t, then you will get the value 1. So with this kind of stuff, that this integration becomes, if tau is smaller than or equal to t, you will have the value 1, which means this h of tau survives. Then, if tau is bigger than t, then you will have none, because you will get 0 for this u. So with this property, this integration will be from minus infinity to until t, right? Because until t you will have 1. So with this range, you will have the value 1 for this u, and since you're multiplying something by 1, you can just write down something inside this integration. Okay, so this property gets involved from here to here. And I already know the function of h of t or h of n because it's a frequency response. Therefore, you just, by doing the integration of this frequency response, you will get this step response of this ideal LPF. Okay, so this is how you actually obtained step response. And let's see the second problem. If you see this step response, you can notify there is quite a lot of oscillation, like this. And in most systems, these oscillations caused by this ideal filter is not very good. Let's say it's a control system that we want to build, and the control system should follow the reference or the command of the signal in a good way, in a stable way. However, with this kind of oscillation, which can be also called overshoot, is very bad for the for the system. So for example, if there is a car with a cruise mode, then if you want to have the velocity of, I don't know, like 60 kilometer per hour, and you try to obtain that 60 kilometer per hour, but if you have this oscillation, which means there is a oscillation on the speed of a vehicle, then it will not be that stable, and the machine or human inside the vehicle will feel very uncomfortable. Mostly it has a problem with a stability. So with this kind of oscillation, it is very bad for most of this system. So the problem number 2 for this ideal filter is that there are some oscillation in time domain, and this is caused by ideal filter. And in most systems, we never like oscillations in time domain. Especially if we are talking about control systems. You have to like smoothly follow the reference or the command, not by just having these overshoots. Okay, there are 2 problems. So we don't know where to cut with the ideal filter, and also we have these oscillations. However, the biggest problem of all this filtering system should be operated in real time. And if you want to apply this system in real time, it should be causal. However, this ideal LPF, the impulse response of this ideal LPF is non-causal, therefore it cannot be utilized. So causal meaning that the system depends only on present and past values. Of the input system, remember? We did this since chapter 4. But as we already studied that this h of t, the impulse response, is non-causal, so it cannot be used. So with these three problems, practically ideal LPF is not used, and the people started to approximate it. So we are gonna adopt the model of the approximation to this ideal LPF, such as the thing that we saw with the previous example, like this. I told you that this example we have the approximated version of LPF for the upper one and approximated high pass filter for the bottom one, right? So this is the approximated version of LPF. Okay, so there's absolutely no difference between the continuous time and the discrete time other than small omega and large omega. So I'm just gonna stick to this figure because they are exactly the same figure, which has the exact same meaning. Okay, first of all, you have the graph for 0 to, so like a positive omega side is visualized with this figure, okay? And notify that this is the magnitude. And if you carefully look at this curve, and if you compare it to the ideal LPF, then first of all, you do not go from passband to stop band immediately, but there is a gradual transition part. Whereas in the ideal LPF, you go from passband to stop band all in a sudden. However, there is a gradual decrease, which is called the transient part, and we have now two cutoff frequencies. We have omega p, which is called the passband cutoff frequency, and omega s, which is a stop band cutoff frequency. And it's ideal LPF is a shape of the rectangular, and this causes this kind of oscillation in time domain. So to prevent that, the approximated version is made of this oscillatory shape, so that if you do the inverse Fourier transform, you will not get the oscillatory trajectory for the h of t. So that's the reason. And these so these delta 1 and minus delta, so delta 1 and delta 2, which determines this omega p and omega s. These are the design parameters for the engineers to construct this approximated LPF. And as you try to have small amount of transition part, as you try to cut this filter in a sharper way, then the problem that we saw, these three problems that we saw with the ideal filter starts to occur. So to okay, so the things that I said, I will write down. So like from passband to the stopband, you have a gradual transition. So this is the big difference compared to the ideal one. And this omega p, I'm just gonna write down it right here. So this omega p is a passband cutoff frequency, whereas this omega s is a stopband cutoff frequency. And compared to the rectangular shape in ideal function, ideal LPF, this approximated version has this oscillatory shape in the Fourier transform. So this will prevent us from having the oscillatory trajectory in the time domain, which was the problem number 2. And this delta 1 and delta 2, which determines this omega p and omega s, are design parameters of our filter. And if you design it in a sharp way, not with the gradual transition, but in a rapid transition, then the problem starts to occur, which we have seen in the ideal filter. So this approximated LPF, we can witness them in the RC circuits. So I will have that as an example. So I will have an example of the simplest type. So we should have a voltage and a resistor and the capacitor. So I will have a voltage which I can control it. So this voltage will be an input. So we have Vs of t, and this is R, which is a resistor, and this is called C, which is a capacitor. So we have VR and VC for respectively, and this is called the RC circuit. And RC stands for resistor and capacitor. And by the way, resistor is, I know you already know that, but in Korean it's called 저항기, and capacitor is 축전기. And resistor has the electrical resistance, whereas the capacitor stores electrical energy. Okay, just a brief introduction of the RC circuit. But I want to focus on the property that this RC circuit can be used as a filter. And with the derivation, it will end up with being the approximated version of the low-pass filter and also the high-pass filter. So okay, and in this RC circuit, there are two systems. So the first one has a voltage input and capacitor output. And the other one has the same input, however, the different output. Okay, so with the voltage input and capacitor output, I will denote this system as H1. So we're dealing with a continuous sign, so I will represent this frequency response in omega, small omega. And with the input of voltage input and the register output, I will denote this as H2 of omega. Okay, we know that they will be the LTI system, so the LTI system can be represented by this impulse response, and the Fourier transform of this impulse response is the frequency response, which is written in this capital H. Okay. So I will apply the Kirchhoff's voltage law. Which is about which can be, I need to have a brief, I would like to have a brief explanation of this law. The sum of potential differences, this is known as voltage, right? Around any closed loop is 0. So if you have a RC circuit and if you define any closed loop, then the sum of that voltage will be 0. This is called the Kirchhoff's voltage law. Okay, I think I won't able to finish this example. I'm not able to finish this example because we ran out of time, so I think we will stop for today. So today we enter this filtering part, and we already know the basics. We already know the basic stuff for the filtering, and we have been through the problems of this ideal LPF. So we try to approximate this LPF, and the RC circuit was our first example. Okay, so we will pick up where we left off in the next lecture, and if you have any question so far, please let me know by the email and I will respond as quickly as possible. So thank you very much for your attention, and I will see you in the next video.